Hello, welcome to our third talk of this geometry day. So it's a pleasure to have Alma Albujer from the Universidad de Córdoba, University of Córdoba in Spain. And she will talk about non-degenerate surfaces with the same Riemannian and Lorentzian mean curvature. So thank you, Alma.
Okay. Well, first of all, I would like to thank Fernanda and Wilhelm for the kind invitation. It is a pleasure to participate in these geometry days. And of course, I would have preferred to be there with you, but times are times. Unfortunately, we have these wonderful technological tools that allow us to be like almost together and with an almost normality. So that's great. So as Fernando has said, I'm going to talk about non-degenerate surfaces with the same Riemannian and Lorentzian manifold. This is a joint work, part of a joint work with Fabio dos Santos, Madalena Caballero, and Eva Alarcón. And let me first introduce a little bit the topic. So I suppose you all of you are familiarized with the basic, very basic concepts of Lorentzian geometry. In any case, I will try to introduce them very fast. So in almost all my talk, I would deal with surfaces, so two-dimensional objects in three-dimensional manifolds. And the ambient space could be Riemannian or Lorentzian. So a surface in a Lorentzian manifold is said to be a space-like if the induced metric is Riemannian. So a Lorentzian manifold, a three-dimensional Lorentzian manifold, is just a three-dimensional topological manifold endowed with a semi-Riemannian metric of index 1, so something plus minus. There I have, in this Lorentzian manifold, we have a surface sigma, which is a space-like. That means that at any point P, we have the tangent plane, and the metric induced on the tangent plane from the metric of the ambient space is a Riemannian metric. And so the surfaces are called space-like surfaces. The easiest Lorentzian manifold is by show the Lorentz-Minkowski space. The Lorentz-Minkowski space is no more than the topological manifold R3 endowed with the metric dx squared plus dy squared minus dz squared, where x, y, and z are the usual coordinates. So this is the Lorentz-Minkowski space. And if we, instead of this Lorentzian metric, consider the usual Euclidean metric there, we have the Euclidean space that I will denote with an abuse of notation also by R3. So we have the same topological manifold, R3, endowed with two different metrics. One Riemannian metric, so we get the Euclidean space. One Lorentzian metric, we get the Lorentz-Minkowski space. Therefore, if we have a surface like a space-like surface in the Lorentz-Minkowski space, we can endow this surface here with two metrics, the metric induced from the Lorentz-Minkowski space and the metric induced from the Euclidean space. We have two different metrics on the same topological surface. And so if we have two different metrics, we have two different mean curvature functions. One associated to the metric from the Euclidean space and one associated to the metric from the Lorentz-Minkowski space. Also with an abuse of notation, I would just say the Lorentzian mean curvature and the Riemannian mean curvature. It's not exactly, the name is not the most appropriate one, but I will use those names just to be more clear and to know what I am referring to at any moment. A surface in R3 is said to be minimal if its mean curvature vanishes identically. In general, a hypersurface in any Riemannian manifold is said to be minimal if this function vanishes, and a space-like surface in the Lorentz-Minkowski space is said to be maximal if the same happens for its corresponding mean curvature function. These terms, minimal and maximal, comes from the fact that those surfaces locally minimize or maximize area among other nearby surfaces. Well, so in 1983, Kobayashi studied those surfaces who were simultaneously minimal and maximal in the Minkowski space. And he showed that the only simultaneously minimal and maximal surfaces in the Minkowski space are pieces of space-like planes or of a helicoid in the region where the helicoid is space-like. So we have just these two types of surfaces, which are simultaneously minimal and maximal in the Minkowski space. Of course, a space-like plane, any place whose slope is controlled, and a helicoid. Just take into account that when we approach the axis of the helicoid, a vertical helicoid, when we approach the axis, the helicoid, the surface becomes more and more vertical, so it gets Timelike. However, when we go far away from the axis, it becomes more planar, it becomes more horizontal, and it is space-like. So we could draw a kind of cylinder centered at the axis of the helicoid in such a way that outside the cylinder, the helicoid is always a space-like surface. I'm not going to give the details of the proof of Kobayashi, but I will just say that the key point of his proof is that assuming that you have a simultaneously minimal and maximal surface in the Minkowski space, he proved that the level curve of such surface are always geodesics. Geodesics of the ambient space. And so if they are geodesics of the ambient space, they are the surface is ruled by horizontal rulings. And so the proof follows from the classification of real minimal and maximal surfaces in L3, which of course the classification of real minimal surfaces in the Euclidean space is a classical result by Catalan. The way to extend this result is to try to generalize our ambient space, study similar problems, generalizing the ambient space. And one of the first generalization we can think about is to consider product spaces instead of the Euclidean space. So if we consider M a Riemannian surface, then we can consider on the topological product space n times r two different metrics, the metric gm plus dt squared and the metric gm minus dt squared. So a Riemannian and a Lorentzian metric in the same topological manifold. We have again the same construction. In this ambient space, a group of Korean mathematicians, Kim, Ko, Shin, and Yang, proved in 2009 that if sigma is a space-like surface in such ambient space, and it is simultaneously minimal and maximal, then it should be horizontally ruled by geodesics. So he extended the result of Kobayashi. They extended. And moreover, in the case where the fiber is a space form, so is the sphere or is a hyperbolic plane, they could classify those surfaces as slices or helicoids. This group of Korean mathematicians is going to appear along the talk. Sometimes there are 4, sometimes there are 5, but they are always the same group, because this same group of mathematicians continued studying this problem. And so later they consider a similar problem where the ambient space was the Heisenberg space. The Heisenberg space can be constructed as R3 endowed with this first metric here. This is the Heisenberg space. So again, we can change this sign here and we get the Lorentzian Heisenberg space. So we have the same topological problem with two different metrics and they obtain the same result. They could classify not only space-like but non-degenerate surfaces in the Lorentzian Heisenberg space such that both mean curvature function vanishes identically. They proved that they were horizontally ruled, and in concrete, they should be a horizontal or vertical plane, a helicoid, or a hyperbolic paraboloid. Okay, so What I want to present in this talk is some extensions of this problem. First of all, we were able to complete the classification for non-degenerate surfaces such that both mean curvature function vanishes in any homogeneous three manifold with four-dimensional isometry group. Later on, I will show some properties in the general case where a spherical surface satisfies that both mean curvature function coincides, but they are not necessarily zero. We get some results on the geometry of such surfaces. We cannot yet classify them, but at least we can say something about them. And later I will show, if I have time, I hope so, how we can get some stronger results in the case where the ambient space is a product space. And I will try also to make you understand why can we expect stronger results in the case of product space than in the general case of a homogeneous three manifold in general. The results presented in these talks are partially contained in the following work. I started with this topic after reading the paper of Kobayashi with a colleague from the University of Córdoba, Madalena Caballero. So we started studying some properties of the geometry of such surfaces in the Euclidean space, and the Minkowski space. Later, we generalized to some of the results to general dimension, jointly with Eva Alarcón. We also make something in product spaces, and the work in which I want to focus this talk is a recent work with Fabio dos Santos, where we consider the problem in homogeneous spaces, as I have said before. So let me start now by introducing the spaces, the ambient spaces in which we work. Any homogeneous three manifold with four-dimensional isometry group, it is well known that it is a Riemannian fibration over a space form. Furthermore, the fibers of such fibration are geodesics, and there is a unit killing field, T, which is vertical to the fibers. All these spaces are classified by two constants. The constant kappa, which is the Gaussian curvature of the space form that appears in the fibration, and the bundle curvature of the fibration tau. So, attending to these two constants, we can classify the homogeneous spaces in the homogeneous space in 6 different families. So, if tau vanishes, we have a product manifold that it will depend if kappa is negative, the hyperbolic plane times R, if kappa vanishes, the Euclidean space, and if kappa is positive, the sphere times R. And if tau does not vanish, then we have like something twisted, we do not have a product. We have the Heisenberg space when kappa vanishes, we have a Berger sphere when kappa is positive, and we have the universal cover of the special linear group when kappa is negative. The 4 in red are the 4 that were previously considered by Kobayashi and by this group of Korean mathematicians. So although I will work in general, later I will focus on the 2 cases that were still open: the Berger sphere and the universal cover of the special linear group. How can we construct the Lorentzian homogeneous L kappa tau spaces? So in the same way, but just asking the vector field T to be time-like. So we obtain the corresponding Lorentzian manifold L kappa tau. As we want to work together with the 2 spaces, I will denote by m bar epsilon either the space E kappa tau when epsilon is equal to 1, or the space L kappa tau when epsilon is equal to -1. Topologically, they are the same manifold. So when kappa is greater or equal than 0, they are just R3, the Euclidean, R3, the topological manifold R3, and when kappa is negative, we can consider a solid cylinder. And so the difference between both of them, of course, is the metric. So we define over this topological manifold, we define a metric that depends on an epsilon here. When epsilon is equal to 1, we get a Riemannian metric. So we get the space E kappa tau, and when epsilon is equal to -1, we get L kappa tau. When tau is different from 0, it is well known that we can define a canonical frame on such spaces in that way. E1, E2, and E3 are these three vectors here. We need to ask tau different from 0 because in E1 and E2 there is a fraction here that does not make sense when tau is equal to 0. But observe that in any case E3 is well defined as partial offset. And such canonical manifold, such canonical frame is orthonormal both with respect to the Riemannian metric and with respect to the Lorentzian metric. In the case of the Lorentzian metric, if E3 is going to be Timelike, but they are, it is orthonormal with respect to both metrics. And in both cases, E3 is a globally defined unitary Killing field on the ambient space, which is vertical with respect to the fibration we had for the homogeneous spaces. From the fact that T is a Killing vector field, we can easily compute the Leibniz connection of T in the direction of any other vector field X. As we have two different metrics, we have two Leibniz connections, and we can compute both of them. We can see that the expressions are quite similar, but they are not the same. They are expressed in terms of this vectorial product here. And, well, there are some difference between them. On the other hand, any vector field on our ambient space can be decomposed as its vertical and its horizontal part, where the vertical part is just the projection onto the Killing vector field T, and the horizontal part the orthogonal one, of course. And attending to this decomposition, taking into account this decomposition and the form of the metrics of the Riemannian and the Lorentzian metric, we can give two nice expressions when we combine these two metrics. So if we consider two vector fields, X and Y, and we consider the metric tensor applied to these two vector fields, and we add both metric tensors, we have that it only depends on the horizontal parts of X and Y, because the vertical ones are cancelled. But when we take the difference between these metric tensors, what we have is precisely the product of the vertical parts. What it is cancelled is the horizontal one. Okay, so we have this nice relation between the metrics. We can compute also the Lie brackets of the vector of the canonical frame. That again only makes sense when tau is different from 0. And from these Lie brackets, we can compute, and this is quite interesting, we can compute the Leibniz connection with respect to both metrics, with respect to the Riemannian and to the Lorentzian metric, when we take any combination of two vectors of the canonical frame. So we have E1, E2, and E3. We get 9 different combinations. So we have the expressions in this boxed. We have this box expression. So the first box is for the Riemannian Leibniz connection. Let me say in that way, and the second one for the Lorentzian one. So E3 is the Killing vector field is vertical. E1 and E2 are horizontal. So the expressions in blue only involves horizontal vectors. The expression in orange involves vertical one, and the expression in black involves a combination of a horizontal and a vertical vector field. So observe that the expressions in blue and the expression in orange coincide. So the Levi-Civita connection coincides when we restrict ourselves just to horizontal or to vertical vector fields, but we have some difference when we mix vertical and horizontal vector fields. In general, if we take two vector fields x and y, we can consider the difference of this of the Levi-Civita connection, and we have that the difference is this expression W here. That of course it depends on two factors, and each one of these two factors is depends on the horizontal part of x and the vertical part of y, or vice versa. Observe also this expression is also valid for tau equal to 0, and of course for tau equal to 0 this expression vanishes. Okay, that means that for tau equal to 0 the two Levi-Civita connection coincide. And this happens in tau equal to 0 is the case of product spaces. So for product spaces, both Levi-Civita connection coincides, and that makes computation much more easy, and that allows us to obtain stronger results in the case of product spaces. In the general case, we have to act more carefully because we have this difference between the Levi-Civita connection that makes things a little more trickier. Okay, so we will consider non-degenerate surfaces in the Lorentzian homogeneous space. A non-degenerate surface in a Lorentzian homogeneous space has two possibilities. It can be either a space-like or time-like. If it is a space-like, then it is well known that there is a unique globally defined time-like unitary normal, which is in the same time orientation of the Killing vector field T, and so this inequality is satisfied. The product, the Lorentzian product of the normal vector with the Killing vector field is always less or equal than -1, so in particular is negative. And in fact, this product measures the hyperbolic angle between these two vector fields. And in the case where sigma is time-like, we cannot assure that there is a unique globally defined time-like or space-like normal, but we can assure that almost everywhere there is, at least locally, a unique space-like unitary normal vector field, such that the same inequality holds. So such that the product with the Killing vector field is less or equal than 0. Why I'm saying almost everywhere, because imagine you have like kind of a non-straight cylinder, and I take a point like that, for instance. In that point, if we assume that the Killing vector field is upwards directed, in that point, if this is the Killing vector field is tangent, so the normal would be orthogonal to this Killing vector field. And if I take a neighborhood of this point, at any neighborhood of this point, would it be possible to have this inequality here? So there can be some curves, some points, some curves in our surface in which we cannot even locally define a space-like unitary normal vector field such that this inequality is satisfied. But we cannot do it, we can do it almost everywhere, because the set of points where this condition holds is dense on our surface. So let us denote by sigma hat this dense subset, this open and dense subset of sigma where this condition holds. In order to work together with the two situations, I will denote by epsilon n the causal character of the normal vector field to the surface. So epsilon n will be 1 if the normal is space-like, that is, if the surface is time-like, and it will be -1 in case where the normal is time-like, so the surface is space-like. Well, so if we have a non-degenerate surface in L kappa tau, we can consider also sigma as a surface in A kappa tau. So we again have the same topological surface with two different metrics. One, which is always Riemannian, which is the metric endowed by A kappa tau, and the other that can be either space-like or Lorentzian, depending on the causal character of the surface. Let us obtain now some relation between the extrinsic geometry of both surfaces, because our last objective is to compare the mean curvature functions. So first of all, we can compare the normal vector fields. We have two normal vector fields, the normal vector fields with respect to the Lorentzian metric, and the one with respect to the metric from E kappa tau. And so we can check that if this inequality is satisfied, then we can always write one of the two normal as a linear combination of the other normal vector field and the Killing vector field G. So we have this nice relation between the normal vector fields. And furthermore, the NR, so the normal with respect to the metric induced from A kappa tau, is going to satisfy this inequality here. So we only can have this equality locally in a first moment, but we can extend it, this equality, to any connected component of sigma hat, of this dense subset where this equality could be achieved. Well, from this relation between the normal vector fields, we can take products with any vector field V. And so if we take the product of NR with respect to the metric R and the product and the product of NL with respect to the metric L, we have this equality. They are the same up to a function that we have control in some way. And when we saw this equality, we thought about the concept of a constant angle. A surface is said to have constant angle if the normal makes a constant angle with respect to some distinguished direction, in this case with respect to the Killing vector field. And so from that expression, we could prove that a non-degenerate surface in L kappa tau has constant angle if and only if it has constant angle as a surface in E kappa tau. Well, this is a first result. I will continue. So if we have the relation between the normal vector fields, the following step is trying to relate the shape operators. So the shape operators appears naturally from the Gauss and Weigarten equation. So we have two metrics. So we have two Gauss and Weigarten equation. We have the Gauss and Weigarten equation related to the metric R and the Gauss and Weigarten equation relating to the metric L. So the shape operators are naturally defined by the Weigarten equation. And from then, with a straightforward computation, we can get the integrability equations where we have derivative connections on sigma when we consider the metric R and when we consider the metric L. So here we have the derivative connection of TR with respect to any vector field X, where TR is just the tangent part, the tangential, the projection of T onto the tangent plane of the surface with respect to the metric R, and TL is the same with respect to the metric L. And it also appears the operator GR, where GRX is nothing more than a rotation of pi over 2 in the tangent plane to the surface, the same for GLX. Okay, so we have this expression, and with this expression, I'm making some computations. We are able, I'm not going to get into the details, it doesn't make much sense, but using this kind of formula, we get the relation between the shape operators of both surfaces. Again, this formula is held in any connected component of the sigma hat, but then by continuity we can extend it to the whole surface. Once we have the relation between the shape operators, we only have to take traces and we get the corresponding relation between the mean curvature functions, which was our goal, to relate the mean curvature function of such surfaces. So what we have is that if sigma is a non-degenerate surface in El kappa tau, then we can write any of the mean curvature function in terms of the other, and in terms of this term here, this one or this one, okay? And these are just the normal curvature in the direction of TL or TR when we consider the corresponding metric. So observe in particular that if both mean curvature function vanishes, these two terms should also vanish, which means that TL and TR are asymptotic directions on our surface. And furthermore, if we know that one of these mean curvature function vanishes, and we know that TL or TR are asymptotic direction, we'll have immediately that the other mean curvature function should also vanish. The only we have to do in order to prove these formulas is to take traces in the expression related to shape operators, but we have to be careful and we have to take an orthonormal basis with respect to the Riemannian metric, which diagonalizes the Riemannian shape operator, because we can only be sure that the Riemannian shape operator is diagonalizable. We cannot be sure that in the case of a Lorentzian manifold, a Lorentzian surface, the shape operator does not need to be diagonalizable. So we only have to be a little bit careful with that, and we get this expression. Okay, so let me give now the ideas to prove our first main result, that it is the generalization of the works I stated at the introduction. So let me show that if sigma is a non-degenerate surface in El kappa tau, and if it has zero mean curvature with respect to both metric, then it is ruled. In order to prove it, we'll consider a point in sigma such that TR at this point does not vanish. That is, such that the Killing vector field at this point is not normal to the surface. We'll work at this point and we will extend by continuity to the rest of the surface. Okay, but we will start working at that kind of point. So we consider a point where this happened. Since we are assuming that both mean curvature functions vanishes, we have that TR is an asymptotic direction, so this term vanishes. But since the Riemannian mean curvature vanishes and this term vanishes, it should also happen that this term should also vanish, since GRTR is the orthogonal to TR. So the sum of them is 2 times the mean curvature. So this 2 term vanishes, which means that the shape operator can be written in this simply form for this vector field TR and GRTR. Okay, what I'm going to show is that the integral curves of the field GRTR are pre-geodesics. And so they would be the ruling of our surface. In order to show that they are pre-geodesics, we have to compute this Levi-Civita connection. We have to derive this vector field in its same direction. So we apply the definition of GR, it was the rotation of the tangent plane, so it's just this product here, this vectorial product. And now we apply the Leibniz formula for the derivation for the Levi-Civita connection, and we have these 2 factors. I will deal with each one of these 2 factors separately. First of all, I will consider the first factor. So we have here we are taking the derivative of the normal. So this is just the Weingarten equation. This says that it is just minus this term in red, the shape operator. So it is proportional to TR. As it is proportional to TR, vectorial product TR vanishes, so the first term vanishes. We only have the second one. With respect to the second one, we can compute it using the Gauss equation. So we apply the Gauss equation. We have the tangent part and the normal part. The normal part is going to vanish when we take the product with the normal for the same reason. Normal vectorial product normal vanishes. So we only have to take care of the first part. And by the integrability equation, we can write the first part, this Levi-beta connection on the surface. In that way, in terms of the shape operator and of the operator of the rotation operator. And so we see that this first factor is a multiple of TR. So the second factor is going to vanish when we take the vectorial product, and the first factor, TR, when we take the vectorial product with NR, is going to be a multiple of GR-TR. So this is just alpha GR-TR, which means that its integral curves are pre-geodesics, so the surface is ruled. Furthermore, it's horizontally ruled because this vector is always horizontal by construction. Okay, so we have proved in a general context that such surfaces should be ruled, but I want to recall that there were two cases where the classification of simultaneously minimal and maximal surfaces was not completed. That was the case of the Berger sphere and of the universal cover of the special linear group. So let us see how can we complete it using our result. So the Berger sphere can be seen as a topological the 3 sphere as a hyperquadric of the complex plane, where we consider these 3 vector fields. And with this contraction, the Berger sphere is S3 endowed with the only Riemannian metric, which makes x1, x2, and x3 an orthogonal frame, such that the first 2 vector, the norm of the first 2 vector is 4 over kappa, and the norm of the third one is this quantity here. If we consider the same, but the same construction, but asking the third vector to be timelike with the same norm, we will have the Lorentzian Berger sphere. The Hopf fibration is well known, that has this form here. And the vertical unitary Killing vector field to the fibration is just the normalization of the vector field x3. Okay, so in that context and with this model of the Berger sphere, we go back to this group of Korean mathematicians of the beginning, and they classified all rule minimal surfaces in the Berger sphere. And they show that a rule minimal surface in the Berger sphere should be congruent to an open subset of a generalized helicoid given in that way here, where this is a family depending on the parameter alpha. In their proof, they show that these rule surfaces are in fact horizontally ruled surfaces, that the coordinate vector field xt is horizontal, and both coordinate vector fields are orthogonal. So using this, we are able to show that, in fact, this family of surfaces are the only non-degenerate surfaces in the Berger sphere, such that both mean curvature function vanishes and there are no more. So how can we do it? By our previous result, we know that any non-degenerate surface in the Berger sphere which has both mean curvature function equal to 0 should be a rule surface, and then in particular is a rule minimal surface. So by the above theorem, it should be one of these surfaces of this family. So we only have to show that these surfaces there are also maximal, and we can do it. Okay, so to see that they are maximal, as we know that they are minimal, we only have to check that the direction TR is an asymptotic direction. And so by the relation between the mean curvature functions and the fact that TR is an asymptotic direction, we will have immediately that those surfaces are maximal. Okay, so in the proof of the result of this Korean mathematician, they also proved this equality here, where this is just the normal to the surface. And so using it is quite easy to show that XS is an asymptotic direction and TR is in fact parallel to XS, so TR should also be an asymptotic direction, and then the surface is maximal as we wanted to show. In the case of the universal cover of the special linear group, something similar happens. The special linear group can be identified, can be naturally identified with a unitary special group. And the metric we have to we have to put on this special unitary group in order to have the homogeneous space is the one that makes these three vectors, x1, x2, and x3, an orthogonal basis in a similar way as we made with the Berger sphere. So the universal cover of the special linear group is isometric to the special unitary group endowed with the unique Riemannian metric such that x1, x2, and x3 is an orthogonal frame with this, where the vectors have this norm there. And again, if we consider that x3 is a Timelike vector field, then the only Lorentzian metric that makes possible this fact is the one that makes our space the Lorentzian homogeneous E kappa tau. In both cases, the normalized x3, so the vector t written in that way, is a vertical unitary Killing field. And in order to prove our classification, we have another result of these Korean guys that is similar to the case of the Berger sphere. It seems a little bit more tricky maybe, but this is just because of the space where we are working now. So we have four basic curves in the unitary special group, which are these curves here. And so they prove that any real minimal surface in such homogeneous space is congruent to an open subset of one of these parameterized surface in that way, okay, where A is any element of the unitary special group, and the other elements here are curves of the kind of above. So according to the result, we can prove, following the same proof as in the case of the Berger sphere, that the only non-degenerate surfaces in the universal cover of the special linear group, such that both mean curvature function vanishes, are locally isometric to an open subset of the above helicoids. Okay, so that's the part I wanted to say for the case where both mean curvature function vanishes. And now I will try to say something in the case where both mean curvature functions coincide but do not necessarily vanish. Before trying to impose this condition and try to impose the fact that they are the same, we need, firstly, we can obtain a relation between the normal curvatures related to both metrics. So if we have sigma non-degenerate surface in one of these spaces, at any point at any direction, at any point P at any direction V, we have two different normal curvatures. The one that we can obtain from the Riemannian metric and the one we can obtain from the Lorentzian metric. So given P and V, we can consider any smooth curve, alpha, with these initial values. And so we have the classical definition of the normal curvatures in terms of this curve alpha. Of course, they are related in some way. So we are going to have the relation. How can we relate it? In order to relate it, we see that TR and TL are just the normalization of alpha prime with respect to the metric R or with respect to the metric L. So they are almost the norm, the same vector, they point to the same way. And so we can compare the Levi-Civita connection of alpha prime in the direction of alpha prime with respect to both metrics. This one was of the formulas I obtained in the first slides, where it appears this function W. So when we compare these two Levi-Civita connections, it appears here this term that of course it involves the horizontal part of alpha prime with the vertical part of alpha prime. And we can just make some computation here. I'm not going to get into the details because I prefer giving only the ideas, but we can, using the relation between both metrics, we can, write the vertical part in terms of the Killing vector field, and we can get some relation. We take the product with respect to the normal. We consider some relations between the metric L and the metric R. And in the end, considering all the relations, we get this formula which relates both normal curvatures. So we can write, for instance, what I'm going to call the Lorentzian normal curvature at any direction in terms of the Riemannian normal curvature in the same direction, and in terms of this product here that observe that the two vectors in the product, the two vectors at which I am considering this metric tensor, are orthogonal with respect to the Riemannian metric, but I am considering the product with respect to the Lorentzian metric. So this term here do not vanish in general. Okay, so we get the relation. Using the relation, we can now we can now obtain some consequences, but now for the case of space-like surfaces. From now on, I will consider a space-like surface, not a non-degenerate one. So it does not hold, our technique does not hold now for time-like surfaces. And let us prove that if sigma is a space-like surface such that both mean curvature function coincides, then the shape operator is nowhere definite. That is, not all the principal curvature of the surface have the same sign. In order to prove it, in order to calculate, to compute the mean curvature function, we only need to have an orthogonal basis. It does not matter which basis it is. If it is orthogonal, it is enough. And we get the semi-sum of the normal curvatures related to the vector of this basis. So the idea is to consider a basis, BW, which is orthogonal simultaneously with respect to both metrics. And so we have the normal curvature is going to be different from respect to one metric and to the other, but we can relate these normal curvatures using the relation that I show in the last slide. Using the relation, we can relate these mean curvature functions. So again, we will work at points where TR is different from 0, so where the tangent space is not horizontal, and we will consider V, the normalization of this TR with respect to the metric, to the Riemannian metric. Then, if we consider W, the rotation of V, so the orthogonal vector to V at the tangent plane, then VW is orthogonal with respect to both metrics. It's not orthonormal, but orthogonal. And for the case of the Riemannian metric, is orthonormal, not only orthogonal. And for the case of the Lorentzian metric, W is unitary with respect to W is unitary also with respect to the Lorentzian metric, and V is not unitary, but it has this expression here. It's 1 over omega L squared that appears before, and it was a quantity that we have control. It was always greater or equal than 1. So we can apply the last expression that relates the normal curvatures to these two directions, V and W, and we get this relation here. So we have that the normal direction with respect to V, if we consider both normal curvatures, they are going to have different sign. The same with respect to W. And so, taking into account that both mean curvatures are the same, we should have this expression here, and combining these three expressions, we finally get that we can write the normal curvature, the Riemannian normal curvature in the direction of V in terms of the Riemannian normal curvature in the direction of W, and we check that they cannot have the same sign, because this term here is always positive. Okay, so we get that the product of these two normal curvatures is always less or equal than 1. We had this for a specific pair of normal curvatures. So in particular, it should hold the same inequality for the principal curvatures of the surface. Okay, so let me show in 5 minutes some results related to the case of product spaces. And let me show how, as I was saying at the beginning, we can get stronger results when we restrict ourselves to the case of product spaces. So the case where tau is equal to 0. So here, I'm not going to take homogeneous spaces, just a product space, and in general dimension. So we'll consider Mn, any Riemannian manifold, and we can construct the Riemannian and the Lorentzian product space in that way, where the factor R can be space-like in the case of the Riemannian product space, or time-like in the case of the Lorentzian one. And so it is possible to prove, for instance, the equivalent as before, where we say that any simultaneously minimal and maximal surface should be ruled in the homogeneous space, is here that the level sets of a simultaneously minimal and maximal hypersurface in the product are minimal hypersurfaces on Mn, on the fiber, anywhere they are well defined. To do this, from the fact that both mean curvature function vanishes, we can see that we can write the mean curvature of every level set that I denote like h of c in terms of one of these two mean curvature, HL, for instance, and so if HL vanishes, HC must also vanish. Furthermore, they are not, the level sets are not only minimal of as hypersurface of the fiber, but they are also minimal are hypersurfaces of the surface sigma with respect to both metrics, both the Lorentzian and the Riemannian metric. The result was obtained not only for, I obtained the result with my colleague, Madalena Caballero, but the result was obtained also by Luis, Fabio, and Eva Larcon in an independent and simultaneous way. Okay, but in the result, we are asking to both mean curvature functions to vanish, and in the same way as in the homogeneous case, we could say something in the case where both mean curvature were the same, but not exactly 0. Here we can also say something and something similar. So we can prove the analogous result that if sigma is a space-like hypersurface such that both mean curvature function coincides, then not all its principal curvatures have the same sign. The idea is the same because the relation between the normal curvatures is now very simple because tau is 0. So it becomes this very simple relation here. So the idea is considering a basis of the tangent space, of the tangent such that the first n-1 vectors are horizontal vectors. And so we do the same, similar computation as before, and we get the result. But what we want to show is that we can combine our result with a classical result of Osserman. Osserman in 1971 proved that given sigma, a compact hypersurface in the Euclidean space with non-empty smooth boundary, then if sigma is not contained in the convex hull of the boundary, then it necessarily has an elliptic point. Our result in the case of the Euclidean space, so if the fiber Mn is Rn, we have here the Euclidean or the Lorentz-Minkowski space. So our result in the case where M is Rn says that not all the principal curvatures have the same sign, which is equivalent to say that there are no elliptic points. Okay, so combining our results with the result of Osserman, we proved in the case of the Lorentz-Minkowski space that if sigma is a compact space-like hypersurface with a non-empty smooth boundary and such that both mean curvature function coincide, then sigma is contained in the convex hull of its boundary. Okay, I will only show a last result in the case where we have a product and the fiber is parabolic, and I will end with that. So I will end with that slide. Let us recall that the manifold is said to be parabolic if any non-positive subharmonic function in the manifold is constant. In that, under this assumption of parabolicity of the fiber, we could also get a result related to those manifolds which have the same mean curvature. And well, we get a general result for products, which is the one that I am showing here, but I will say just the corollary in L3. We proved as a corollary of this theorem that the only entire scalar graphs in the Lorentz-Minkowski space bounded from above or from below by a scalar hyperplane and such that both mean curvature functions are the same and greater or equal than 0 are vertical translation of such a hyperplane. So under these assumptions, we can get a kind of rigidity result for these surfaces. Well, I will end here. Okay, I will have something else, but I will end here. So thank you very much. That's all I wanted to say.